We're going to talk about dynamic similarity, the importance of non-dimensional numbers I've found as I've worked with many of my students in research that we tend to really unappreciate the need for non-dimensionalization. And I hope some of these examples today will help motivate. Here's some of the power of and the importance of non-dimensional numbers. You've all seen various non-dimensionals before. I'm just pulling up my screen here. Just give me a sec. And I've done things like Buckingham pi theorem. We're not going to look at that, but really more the concept of non-dimensionalization. In fact, that theorem is often not needed. Usually we can deduce non-dimensional groups pretty easily. Let's just jump into an example here. Let's discuss this wind turbine. And let's say we were really interested in predicting the power that this turbine produces, and we've identified the two key parameters are one, this rotation speed, how fast the blades rotate, and another is the incoming wind speed. And we've decided to set up an experiment. We're taking this down to our wind tunnel, and we're going to vary the wind speed through a bunch of speeds in this range of 5 to 15 meters per second, and rotation along this range. The specific numbers here are not important, but rather just the idea that these are two parameters that we're going to change. And in fact, we're going to assume here that we don't really know anything about the aerodynamics. We're going to just treat this like a data scientist and just try to look at some input-output relationships. So here's what this looks like. Went out and say we did all these experiments, and we have this data. In this case, we chose them basically randomly, and I've plotted them on two different plots. Although of course both speed, free stream speed, and rotation speed are changing at the same time. And it appears that there's not some very clear relationships, other though we do see appears that there's a limit. So at least I could perhaps predict what the maximum power that you might produce is for a given speed. But beyond that, it seems as if that's really hard to discern any sort of relationship. And in fact, what we're looking at here is that we're trying to predict power, right, as a function of free stream speed and rotation speed. Of course, neither of these are non-dimensional numbers. So we don't expect to have universal behavior. This is going to be very specific. And so perhaps if we non-dimensionalize, we can we can collapse the data perhaps and see better underlying trends. In other words, it may not be V infinity or omega themselves that matter at all, but really specific ratios of these quantities. So this is obviously in units of speed. This is an angular speed, so to get it in the same units, we need to multiply by distance. And we could do anything, but it seems to make sense to use the tip speed. So for example, if this was the hub and this was a blade, right, and it was, say, spinning around this way with some speed omega, then the speed here at the tip, the linear speed, would be omega times r, where r was this radius, right? There's nothing magical about that. We could use anything, but that seems to be a logical choice, kind of looking at that max speed. So we could form a relationship. Let's call this non-dimensional parameter lambda, be a ratio of this tip speed to my forward speed. That's clearly going to be a non-dimensional group, right? Because I've got speed divided by speed. And in fact, this is what the convention is in the wind turbine community. It's called the tip speed ratio. But keep in mind, there's nothing, we could do any other sort of ratio. That'd be fine. It would change some specific numbers, but not the nature of this, these conclusions. So for example, in the rotorcraft community, the inverse is typically used, whereas in the propeller community, it's the inverse, except for the rotation is usually in rotations per second rather than radians per second, and often the diameter is used instead. And so those two relationships actually just end up being inverses with a factor of pi. Not really important, just to say that this is not unique. Similarly for power, so we've non-dimensionalized our inputs. We need to non-dimensionalize power, so we have a fully non-dimensional relationship. Power, of course, is a work per time or a force times velocity. We've already seen a typical way to non-dimensionalize forces, right? If we're thinking about a fluid, we'd often use a pressure, a dynamic pressure times an area. So for example, we could use a dynamic pressure times an area. Again, there's no unique choice on the area, but what would seem to be a logical one is to use, say, this area, right? The area swept out by my blades, which is pi r squared. So let me get rid of that. So let's put a pi r squared. Again, we could choose other things, but that's a pretty logical scaling thing. We'd expect that power would change as that area grows. But this is now a force, right? Because I've got a pressure times an area, so I need another velocity. So let's just change this v squared to v cubed. Oops. And that then is non-dimensional. And this is a convention that's used. This is called the power coefficient. So now we are now trying to predict a non-dimensional quantity power coefficient as a function of a non-dimensional input tip speed ratio. So let's go back. Let's take that exact same data, but instead of plotting it this way, we'll plot it in terms of tip speed ratio. We'll take this power and non-dimensionalize it. And this is what we get. Now we can see some very clear structure, right? There's some noise there, but there's clearly some sort of underlying behavior. And if I gave you input conditions, like I said, we gave you some conditions that we didn't test, a different velocity, a different rotation rate, you could predict the power pretty well, right? We could then compute the corresponding tip speed ratio, interpolate onto this curve, and then get the power coefficient. And then knowing our conditions, right, how big my rotor is, what the density is, I could back out what power I expect to produce. So now I have this predictive model and I really don't have to know anything about the aerodynamics of how wind turbine works. So this highlights, one of the real advantages here of non-dimensional numbers is that we can get to these underlying relationships. Again, it's not really speed that matters or rotation speed, but rather ratios. It's not power that's the fundamental quantity, but rather a non-dimensional version of that that's going to be more universally relatable. But let's do this example one more time. I did up front, right, a whole bunch of random inputs. That's probably not how you would do it if you went to the wind tunnel. Probably more realistically, we'd do something like fix one of the parameters and vary the other. So in this case, let's just pick 4 different rotation speeds. I'll go down to the wind tunnel and just vary the wind speed of the wind tunnel. Okay, and so that's going to look like this. Again, 4 different rotation speeds. I get 4 different curves where I varied the wind speed. Now in this case, I see a little more clarity in terms of relationships, but this is actually more dangerous in some sense, because when I look at this, I get the sense that, okay, maybe I should create a model that, I could fit curves pretty easily to each of these. And I could do so with a separate one for each rotation speed. So maybe I've got kind of this 2-phase lookup model where you give me a rotation speed and I interpolate onto some of these curves, and then I use a fit for each rotation speed. But again, if we normalize the data and just replot, not collecting any new data, just replotting in a different way, we notice that we're actually just not getting separate relationships, just one relationship, but those low speeds were capturing one part of the curve, high speeds another part, and putting them all together, we're capturing this full data trend here. Okay, so this is one of the real powers of non-dimensional analysis. Again, you don't generally need a theorem to figure out non-dimensional groups. We could have chosen other ones, right? Like if I had chosen a different ratio here or a different way to non-dimensionalize this, the numbers would be different. The curve shape might change a little bit, but this underlying functional relationship, right, that there's kind of this one-to-one mapping, a collapse of the data, if you will, would still occur. Okay, so thinking about this more broadly, like in aerodynamics, we often want to understand something like I've got an airfoil here, and there's a free stream velocity, and I want to predict the drag. This is a terrible airfoil. Try and draw it again. Okay, and the drag is a function of many things. We could throw things out. I'm just going to upfront put in geometry as kind of a catch-all for think of attack and the shape and all of that. But for a given geometry, we know there's a lot of fluid parameters that are going to matter. Whoops, like the speed and the density and the viscosity and the speed of sound, perhaps some other things, right? Maybe gravity, but probably not. So again, if we take the same procedure and we non-dimensionalize, we have a non-dimensional drag, a drag coefficient, we expect it to be a function of I'm going to put a star here to say this is a non-dimensionalized geometry. So just, something that's scale independent. The non-dimensional fluid parameters we've seen before, right? We could group these terms here. This is going to give us a Reynolds number. Adding the speed of sound will give us the Mach number. And that's pretty much it for almost every aerodynamic application. For a given geometry, these are the most important. And if it's low speed, then just Reynolds number. Sometimes, like, that wind turbine one, there are other operational things like the tip speed ratio. But, this is pretty much it. If gravity is important, like which doesn't apply in most of aerodynamics, buoyancy is negligible. But if we had like a dirigible, an airship where we're at low speeds, very high volumes, then the gravity term might matter, in which case the Froude number would be important. If there's unsteadiness, we'd have a Struhal number. But this is kind of the power of doing a non-dimensionalization, is that I could take a full scale vehicle, and if I use the same geometry scaled down but the same relative sizing, then if I can match these other parameters, I can predict its performance, in software or in an experiment or something like that. Okay, we'll see that that's actually sometimes harder said than done. Before we do that, I just want to do one last motivating example, one that's a little more mathematical. Let's look at some governing equations. And this is one of a simpler set, restricted 2D, incompressible, but enough to highlight the concept here. These are the Navier-Stokes equations. Okay, so I can apply the Navier-Stokes equations to one of my problems. This is not non-dimensional as described, right? These are certainly dimensions in here, but I could non-dimensionalize this. So let's do that. So for example, just to start, I've got a velocity term here. So maybe I just want to divide everything by velocity, and a good characteristic velocity would be my free stream velocity. So if I divide my whole equation by the same thing, I didn't change anything, right? So I'm going to put a V infinity here in the denominator, and I'll put a V infinity here. I also see a velocity term here, so I'm going to divide by another V infinity, but I'm just going to put this right up next to it in this case. In this term, I'll stick it right here next to that one, so this becomes squared. And then in this term, I'll just put it right here. And the reason why I'm putting it right there is because I'm going to define some new parameters, like U star is my non-dimensional x velocity, and that's going to be equal to U over V infinity, for example, right? So this whole term will become U star. This whole term will become U star. So I'm getting there. I still got this x term here, though, so let's divide by a chord on the bottom. So I'm really multiplying by chord, but because I'm dividing on the bottom. So I'm going to do that on every term. There's an x there. There's one there. There's one there. Okay, so C could be my chord length, right? It's just some representative length. So this whole term is non-dimensional. If I was to write that out, this would look like this is a U star, this is a U star. And if we define x star as x over C, then that first term looks like the partial of U star with respect to x star times U star, right? So it looks the same so far. I've just, but I've made everything non-dimensional. So this one is also non-dimensional. Pressure divided by rho v squared. That's like a dynamic pressure. So we could define a non-dimensional pressure that way. There are generally better ways, but just for simplicity, let's just do that. That'll be my non-dimensional pressure. So then this term becomes P star over X star. And this is already, this is V star times du star dy star. And now this one looks pretty good. This is non-dimensional, this is non-dimensional, but this has two x's here, right? This is x squared. So I'm going to need to divide by another c. I'm dividing on the bottom. So in other words, I'd need to put another c here, right? So it's like putting a c on the top and the bottom here in this denominator. So I've got now this is what's left over, mu, and then this is all non-dimensional. U star, x star squared, U star, y star squared. And I'm sorry, that's a little bit messy, but we can take away our conclusion now. everything looks exactly the same. Like if I had deleted all these stars, this would look exactly like my original equation, except for this term here. Okay, and what is that term? Well, if we look more closely, this is 1 over the Reynolds number. Okay, so in other words, I have a non-dimensional set of equations, and as long as I match the Reynolds number, I use the same Reynolds number, then I am going to get the same non-dimensional flow solution, right? So in other words, again, I'm going to get the exact same solution. In different scenarios, I could have very different velocities or different sizes or different viscosities or whatever. As long as I have the same non-dimensional geometry, right? It's a scaled version of the geometry and boundary conditions, of course. All I have to do then is match the Reynolds number between these two simulations, or simulation in real life or simulation experiment, match the Reynolds numbers, and the non-dimensional flow solution, meaning the non-dimensional pressures, the non-dimensional velocities, will be the same, okay? Now, we do the 2D incompressible Navier-Stokes equations. If we had done the compressible Navier-Stokes equations, then another non-dimensional grouping would have come out, which would be the Mach number. If we had added the gravity term back, then we would have got also a Froude number. If we had added the unsteady terms, we would have got a Struhal number. So again, depending on which terms are important, this again is just another way to illustrate the same principle, that as long as we match these parameters, then we can do experiments or computations with different dimensional values, different sizes, different velocities, different densities, as long as we match the important non-dimensional quantities. Okay, and this is the power of dynamic similarity. It's what allows us to do wind tunnel testing. But even that is not so easy, right? So let's think about Reynolds number, for example. Let's imagine that I've got this big airplane here, and it's flying up there, and I am down here on the ground, and I want to build a little tiny one, right? That I'm going to then put in my wind tunnel and try to predict, forces, drag, lift, whatever, okay? And let's say we'll call this full scale F, and this is the model scale M. Let's say the length or the size of my model is 1/20th of the full scale. Okay, so it's smaller. That's of course typical. That's why we're doing it. We don't want to make this huge thing. We want to make a small one. All right. Well, and I want to match the Reynolds numbers. So I need to have Reynolds number of full scale equal Reynolds number of model scale. So that means I need velocity full, length full over my kinematic viscosity to equal the same thing at the model scale. And it turns out that the ratio, so the kinematic viscosity, excuse me, is actually quite a bit higher at altitude. The dynamic viscosity is higher on the ground because I have higher temperature, but the density drops so much more significantly as I go up, so that the kinematic viscosity is actually bigger up at higher altitude. So the full scale is, say, somewhere between 2 to 3. Let's just say 2 for this example to keep it simple. Let's say it's twice as big as my full scale. Okay, whoops, sorry, as my model scale. All right, so I want to know how fast I need to run my wind tunnel relative to my airplane. So if I take this equation here and I rearrange it, the velocity of my model relative to full scale, that's equal to LF over LM times nu M over nu F, which is, this is LF over LM, that's 20, right? And nu M over nu F, that is 1/2. So that's 10. So in other words, this is saying for me to match the Reynolds number, I need to run my wind tunnel at 10 times the speed that the full scale airplane is flying at, which is impossible, right? That's exactly what I did not want to happen. I wanted to run it much slower. So how do I do that? How do I match Reynolds number? Turns out it's actually really hard, and often we can't. So You might think we could do a water tunnel. Sometimes we can, but generally that's actually worse because even though we get a big benefit in terms of, there's a big density, that's also really hard because even though the density is high in a water tunnel, it takes a lot of energy to move water relative to air. And so actually that's even harder generally to match Reynolds number in a water tunnel. Some solutions that can be done, all of which are expensive, is either I get a way bigger wind tunnel, and they're large ones, right? Like the NASA AIM, which is something like 120 feet cross section. Or I pressurize my wind tunnel. I can change my density that way. Or I use a cryogenic tunnel where I cool it down, right? That can directly change my viscosity, so the temperature. Those are very expensive and also generally lead to smaller models because it's harder, more expensive to pressurize big volumes or cool big volumes of air. I can use different gases too. That's another option. But again, all of these are pretty expensive and pretty limited. So often, frankly, we cannot or do not match Reynolds number. Fortunately, that's not quite as bad as it sounds sometimes. Because if you think about Reynolds number, and this is just to motivate, this is not a perfect example, but remember, you've seen this before, right? If you've seen the drag, let's say the drag coefficient of a cylinder, just a circle, right? So I've got just the cylinder here as a function of Reynolds number. It starts out and kind of drops, and then it flattens out for a while. And then I get to transition going from laminar turbulent, and it drops and then kind of goes up a little bit. This first part where a lot is happening is at very small Reynolds numbers. I mean, very few engineering applications where that's even applicable, right? I mean, a lot of our stuff is here, and then big airplanes, fast things are kind of here, where things don't change very fast. Reynolds number is the one exception generally of all the non-dimensional numbers you'll see. Most are of order 1, right? I mean, lift coefficient, Mach number, pressure coefficients. Most things are order 1. Drag is smaller, but most things don't vary across huge things. But Reynolds number does, right? For a full-scale airplane or a big wind turbine, these are in the millions, tens of millions. Even little small things are hundreds of thousands, right? Like a little small RC plane. Tens, hundreds of thousands. So we're pretty big numbers. These vary across orders of magnitude. So really, sometimes I think of it as it's really the log of the Reynolds number that's perhaps the more fundamental, or is the more typical number that we might use. And that's maybe a reasonable way to think of it, is that we don't actually have to get exactly on. Usually if we're in about the order of magnitude, then we're pretty good. Of course, near transition, that's really hard experimentally. So we either have to, have a big budget for some of these expensive experiments or go to computation. What is important though is we get in the right range, right? Laminar versus turbulent behavior is quite different. So a common thing that's done is that, like say on a wing here, is that in the small scale, or say the large scale, full scale airplane may trip to turbulence very quickly because of the high Reynolds number, which may not happen in the wind tunnel. So often what's done is that like a roughness strip is placed near the leading edge, or zigzag tape, something like that, is placed there so that the flow becomes turbulent very early to kind of mimic the full scale behavior. And so actually we can get away with that often pretty well. Again, if we're not too close to transition. Finally, the last thing I just want to really quickly touch on Mach number. Again, this is a review. I know you've seen this. Mach number is just the ratio of speed, a flight speed, say, to the speed of sound, or the local speed to the speed of sound. A is a common symbol for speed of sound. There is a major physical difference as we cross Mach 1, right? There's actual fundamental differences in the flow physics. But as aerodynamicists, we often use additional categories. These do not have accompanied, exact breakpoints, but are just words that are used to help delineate things. I'll explain in a second here. So for example, we often will call flow incompressible. The real limit is in the limit of Mach 0, right? That's truly incompressible. But typically we would say up to about Mach 0.3. And the reason why we say about Mach 0.3, that's about when the change in density, the change in density is about 1%, something of that order of magnitude. So it starts to become a little bit noticeable, and below that it's very small to negligible. So that's a typical rule of thumb. Again, this is not like Mach 1 where there's a hard transition and things change. This is just a rule of thumb. Subsonic, of course, strictly means anything below sonic or below Mach 1, but often we're kind of referring to things that don't have strong compressibility effects. And so we're typically saying, maybe around 0.6, 0.7. It may mean up to 1, right? This is not a hard number, right? But somewhere in that range. We often also use the word transonic, which means near Mach 1. Sometimes people use it for both below and above Mach 1, but in that range. But perhaps more typically, we would call above supersonic, and we just kind of stick to below 1 here. But again, this could be something above too, is sometimes used. So for example, a transport aircraft will say they fly at transonic speeds, and they're typically in the Mach 0.8-ish range, and this is where, again, the reason why we delineate, this is where no compressibility effects, some mild ones. Here there is, we're kind of at the edge, we're doing what we can to not have strong effects, but there could potentially be some strong effects of shock waves and things like that we'll talk about later. And then supersonic, again, strictly means above Mach 1, but we usually cap it around 5, and above 5, we'll call it hypersonic. Again, nothing magical changes at 5, just a rule of thumb. And the reason why we do that is that around that point, the change in temperature from the extreme speeds becomes very significant. We get a lot of aerodynamic heating, and that changes the nature of the flow field somewhat, in the sense that we get ionization and separation of the molecules in the air. And so we have to start thinking about chemical reactions and things like that. And so, at these very high temperatures, we call it hypersonic. But again, really only at Mach 1 is there a fundamental change, but these are categories that are commonly used. Okay, so next time we're going to talk a little bit about some of the governing equations, derive some of these equations that we use heavily in fluid dynamics.